because they're a lot easier to visualize. Because when you're dealing with quadratics, it's either going to be up like a cup or down like a frown, isn't it? Okay. If you think about what these are, if I look at this simple equation, this one I believe is number 51 on your thing. What I did is I made a photocopy of a lot of the word problems so that way you don't have to write them all down. So I think this is number 51 on the sheet that I gave you. That way you can read it and annotate and do whatever you need here. Just looking at that equation, is that an up like a cup or down like a frown? It's down like a frown, okay? Now, I know that it's going to do that somewhere. Are we okay with that? Now, real fast, when you look at a quadratic equation that's in what we call standard form, what does the value of C afford you? Which intercept? Y-intercept. Right. So I know that the y-intercept, when it's 0, would be 38.8. You okay with that? Bless you. Now, looking at that, that means that I have a 0 that would probably be negative and a 0 that would be positive. Are we okay with that? Somewhere along the lines, the graph's going to have to cross the x-axis. Where it does, I don't know. But the premise here is that I do know for a fact that at 38.8, I cross the y-axis. Just by looking at the numbers, without doing any math. Now, as I go back and reread this, the engine torque in foot-pounds of one bottle of car is given by law, where x is the speed of the engine, RPMs. Find the engine speed that maximizes torque. What's the maximum torque? Now, when you're talking about these things called maximums and minimums, maximums would be where do you think on this graph? The top, the highest point. What is that point called in regard? It's the vertex, isn't it? Your vertex will always be either a maximum or a minimum. Vertex being a maximum is when you are down like a frown. Vertex being a minimum is when you are up like a cup. Make sense? Now, what's great about this is that when you have your vertex gives you an ordered pair, some value of x and some value of y. Now, in this problem, what is the y value? What is the y value about? Torque. The y value is the maximum torque value. The x value would therefore be the RPMs. RPMs to torque. Okay? That's what these types of things allow you to do. Now, we can go through the whole process. We can do the opposite of V over 2A and figure out where the x value is, substitute back in and get the y value. It works, but it's crummy numbers. Why not make it easier on ourselves? Let me show you how you can figure this stuff out via calculator. So take your calculator out and go to your y equals. I'm going to use the fancy color one. Not to see you guys. And I want to put in my y equals. I'm going to substitute in that function that we just got, that negative 3.75 x squared plus 23.2 x plus 38.8. You all right with that? Does anybody not have a calculator today? Very disappointing. This is the work we sat with. It does. Everything. Yeah. All right. Now, Hit the button that says graph then. Exactly. Where'd it go? I don't know. Where is it? Stir yourself like a cup. You know how to go back and overwrite it, so you have to do the whole thing? Insert. Very good. All right. Now, as of right now, you cannot see where that vertex goes because of the way that the resolution is set up. But if you take your calculator and you look, and you tilt it, you should be able to see it up there, the way that it bends itself forward. I get it. I'm joking. Blah, blah, blah. All right. So think about the information that you know. You know that you have a y-intercept at 38, and you see that you have you can see where it crosses your x-axis, which means you have to change your window to see the peak there, don't you? Now, here's where playing around with the word problems takes a little bit of time to get used to adjusting resolutions. If you hit the button that says window, we know that the y-intercept is at like 40. But we also know that it's still increasing after that. You okay with that? So what value do we have to adjust to make it larger to see the graph? The y value. Am I going to adjust the maximum y or the minimum y? Maximum y. So we scroll down to where it says y max, and we're going to adjust it and maybe put in 70 just for a guess, and just re-hit graph. That means you probably put it. You probably put your max at under the minimum as opposed to. It's not up there all the way. So what should we do? Adjust it again. What we're doing here is we're kind of guessing around where the window is, and this happens a lot with these. So we go again and adjust it to maybe 90. You went to 80? Okay. Well, and that's fine if you're at 80 versus 90. Everyone all right with that now? So now we know that in the calculator, it was able to graph that for you, so you don't have to worry about doing any work. But nice. Now, here's what we want to do. We know that at this point, at that vertex, lies the maximum values for x and y. So what we have here on the calculator is a button. Well, I know. Second, calculate.
I have 2 buttons.
Then don't do it. Do it by hand. What option do you think we're going to select here? Maximum. So you can scroll down to the maximum or just press 4. Now, here's where it gets interesting. It's going to ask you a series of questions. What you're going to be doing is on your graph, you have that little cursor. Okay? You're going to adjust your cursor to the right. You're going to move your cursor to the right. And you see how it's asking you the question, left bound? Everybody see that right here? What that means, it's asking you to place the where do you want to place your cursor for it to be a left boundary? What the calculator then does is you place your left boundary here, and then it's going to ask you, bless you, hit enter, and then it's going to ask you your right boundary. So you move to the right of where the maximum occurs just by scrolling over it. What it's doing is that it's checking in this boundary here. It's going to calculate all the possible values in the domain to see which value of the domain generates the largest value range. So it does that for you. The next thing it says, guess. Potato. Hit enter again. There's my maximum. My maximum occurs at x when x is equal to 3.09. That means you put it on wrong sides. And then my y value is at 74.68. So this allows me to say, let me move this in here so you can see it. So that means that my vertex here, the maximum RPM, 3.09, I think it's in thousands, but so, and then the torque is at 74.68 foot-pound. So at 3,000 RPMs, which is kind of low RPM, you have 75 foot-pounds of torque. It is kind of. It is. Well, yeah. For a model car. No, it's for some model car. A model car, like an RC car, wouldn't be anywhere near those numbers. 75 foot-pound of torque at about 3,000 RPM is probably like a small Harley. Okay. A small Harley has about 70, 75 foot-pounds of torque. Okay. You get into a car. I know, like my wife used to have she had a diesel TDI Jetta, and that one had maybe 90 horsepower, but it also had 90 foot-pound of torque because of the diesel engines. Okay. Nowadays, you get a diesel truck. I think like the new Silverado diesel truck will have 700 horsepower and 800 foot-pound of torque. Yeah.
What is that?
It makes things move.
It's how hard
It's what makes the car turn. Horsepower is the engine. The engine turns it into force, which makes it rotate. So, I was trying to relate to what is 75 foot-pound of torque equate to. You guys all know what a Harley looks like, right? A motorcycle. There you go. It's like a small Harley. Yes, sir. Just throw in the charger. If you need. All right, let's go to the next one. Although a football field appears to be flat, its surface is actually shaped like a parabola, so that rain runs off to either side. It's called a crown. You have to keep the cover off, and then just put it into the slots. Be smarter than the machine. Cross section of the field with synthetic turf can be modeled by blah, where x and y are measured in feet. What is the field's width? What is the maximum height of the field's surface? Okay. Again, this generic thing is going to get you to something. Okay. It's going to get us some parabola. It's going to get us, what's that? It's going to get us the maximum height, and it'll also get us the, what do you call it? We have to figure out the width. How wide is that field? Now, real quick, what format is that equation given to you? The not standard one is the second one. It's the vertex form. Very good. That one. Yes. It's the vertex form. So vertex form is y equals a x minus h plus k, or quantity squared, excuse me. Where h and k are your what? Your x and y is your vertex, isn't it? So your vertex here is at 80, comma, 1.5. If your vertex is at 80, where's your axis of symmetry? It's at 80, isn't it? So without having to do any math, we know that $80 is the axis of symmetry, isn't it? Which means that 80 is going to be the midpoint of the zeros. Is your field going underground? No. So no matter what, here to here, the distance from this spot to the midpoint, the distance from this spot to the midpoint, are both going to be equal to what? Well, if 80 is the middle, how much is it from 0 to 80? And how far is it from 80 to the other midpoint? Or not 80, what's the other endpoint? An 80. Which means how wide is the field? The field is 160 feet across. Because if 80 is halfway, wouldn't you just have to go another 80 feet to be at the end? How tall is the field at the height, at the highest point?
1.5.
Done. Didn't have to use your calculator for that, did you? Did you have to worry about anything on this problem? You don't, because the idea is understanding, guys, it's understanding what format things came in. Like she was saying, it's that vertex form. Vertex form of 4, it allows you to notice that you've got an x, y, or your h and your k. When we had the other one a minute ago, that standard form, that allowed us to figure out that we had an intercept at that 38 inch. Bless you, so that we knew what it would look like as we drew it out. Scientists determined the rate of y, calories per minute, at which you use energy while walking can be modeled by where x is your walking speed in meters per minute, because everybody talks about meters per minute. Graph the function given domain, describe how energy changes as walking speed increases, what speed minimize energy use. All right, this one's a little bit different because what is it telling you to do? Is this up like a cup or down like a frog? It's up like a cup. It's up like a cup. It's up like a cup. Where's your vertex? Okay. That's your vertex, because that's your H and K. Now, before we get too far, it said that what speed minimizes energy use? Well, remember, y is the energy, x is your speed. What speed minimizes your energy use? 90. X is y, minimizes it right there at that value. If you walk that slowly, that's the whole point here, guys, is understanding what this means. This y value is your energy use. X is your speed. This is the vertex. That's a minimum because it's up like a cup. Okay? It's the idea that all you're doing is pulling information from it. Okay? What happens as you speed up in your walking speed? You use more energy. Boy, that was tough.
No, use more energy. Look at the graph.
The car dealer that I did a commercial for when I was a kid, he went to yes, he went to jail for turning back odometers. Well, nowadays you really can't do it. It's programming. You'll see that it's been messed with, but back then you could actually break into the systems and train. Are you using a screwdriver to make go-fast holes? Yes, because you just open up the engine while it's running and you just pour alcohol into it. It just makes it go faster. It's like,
It's gotta have that like
oh yeah, yeah. And with a big guitar. That's good. That's good. All right. So the woodland jumping mouse, because they're a thing. And sometimes it's nice to have a good picture. That means I don't have to drive because my awesome drawings are awesome. The answer to that one, there's your answer. It's the minimal. Yeah. Exactly. And that's the thing. And guys, you brought up a great point. A lot of times these things are so much easier than they need to be because the answer is right. If you understand what format you're in, you get this. Now, obviously, the domain restriction here meant that you're not going any slower than this, you're not going any faster than that, but it's still within that domain that value occurs. So you didn't have to worry about it. So let's look at the woodland jumping mouse. Can hop surprisingly long distances. A relatively long hop can be modeled by that, where x and y are measured in feet. How far can a woodland jumping mouse hop? How high can it hop? All right, now this next one, is that written in a format that we've used? No. Could you distribute and do all that work if you wanted to? Bless you. Yeah, but let's not. So let's go right to our calculator. In this case here, again, since we don't have a